Hi guys, this is AS Chemistry, Organic Chemistry, and we are doing alkenes. Question 11. Compounds containing the allyl group CH2 double bond CH2 have pungent smells and are found in onions and garlic. Allyl alcohol is a colorless liquid which is soluble in water. Allyl alcohol behaves as a primary alcohol and as an alkene. Give the structural formula of the organic compound formed when allyl alcohol is reacted separately with each of the following reagents. So the first reagent is bromine in an inert organic solvent. So adding bromine results in the reaction of bromine with the alkene group of allyl alcohol. So bromine will add on to both the carbon atoms having a double bond between them, forming the compound CH2Br. Then it will be single bonded to CH Br, which will be single bonded to CH2OH. Next, it will be reacted with cold dilute acetate potassium manganate 7. So if it is cold and dilute, then OH groups will be added onto the two carbon atoms with a double bond between them, which means the structure will be similar to the one formed with bromine, but instead of Br, we will have OH attached to the same carbon atom. So the product here would be CH2OH bonded to CHOH, which will be bonded to CH2OH. And next we have the reaction of allyl alcohol with hot concentrated acidified potassium manganate 7. So in this case, we will have the double bond completely breaking, resulting in the formation of CH2 and double bond O in the case of the species on the left side of the double bond, and on the right side of the double bond we have got C double bond O single bond H attached to CH2H, which is a primary alcohol which is also oxidized to C double bond O single bond H. So dial forms. So the aldehydes which are formed are both oxidized to their corresponding carboxylic acids. In the case of methanol, which is a single carbon aldehyde, it is oxidized to HCOOH. And in the case of the ethane 1,2-dial, the two carbon containing aldehyde is converted into COOH bonded to COOH. This carboxylic acid is known as ethane 1,2-dioic acid or oxalic acid. And both the carboxylic acid that we have obtained undergo oxidation. And both are oxidized to carbon dioxide and water. So methanoic acid is converted into CO2 and H2O, and ethane 1,2-dioic acid is converted into 2 moles of CO2 and H2O. So in total, the final product upon reaction of allyl alcohol with hot concentrated acidified potassium manganate 7 is the carbon containing product being carbon dioxide and the other product being water. So CO2 and H2 are the final products of this reaction. Question 12. Under suitable conditions, propene and cyclopropane each react with chlorine. With propene, 1,2-dichloropropane is formed. So the double bond is used up, as in it opens up, the pi bond is broken, and two sigma bonds with two chlorine atoms are formed by the two carbon atoms that had a pi bond between them. So state fully what type of a reaction this is. So this is the addition of chlorine onto propene. So this is known as electrophilic addition. Question 13. S, T, and U structures are given. It is possible to convert S to S, T, or U into one another. Okay. State the reagents and essential condition that would be used for the following conversion. S into T. So S contains two carboxylic acid groups and an alkene group, while T contains two carboxylic acid groups, so nothing happens to them, while the double bond between the two carbon atoms is added on by a hydrogen on one carbon atom and an OH group on the other. So this is basically hydration reaction taking place. So we need to state the reagents and essential conditions. So the reagent here would be water because hydration is taking place, and the essential conditions would be H3PO4 catalyst, SiO2 should be present, 70 atmospheric pressure should be present, and 300 degrees Celsius temperature should be there in order for this reaction to occur. And water would be present in the form of steam at 300 degrees Celsius. Next, we have conversion of S into U. So the difference between S and U is both the carbon atoms having a double bond between them are added on by two OH groups. This can only happen when we react S with cold, dilute, acidified KMnO4. Two OH groups will be added onto the two carbon atoms that have a double bond between them. Then we have conversion of T into S. So T contains two carboxyl group and an OH group, while S contains two carboxyl group and a double bond. So conversion of T to S is dehydration, and dehydration requires two different conditions. Any one can be used to carry out dehydration. The first one is reacting with Al2O3 at 350 degrees Celsius temperature, or we can have concentrated H2SO4 at 170 to 180 degrees Celsius to carry out the dehydration reaction. Question 14. Explain how and why bromine can be used to distinguish between an alkene and an alkane. So, aqueous bromine at RTP when added to alkenes become decolorized as both Br atoms add onto the carbon-carbon double bond via electrophilic addition, while UV light is required for Br radicals to get substituted onto alkane molecules. So in this way, bromine can distinguish between alkene and alkane the way it reacts with the organic compound. Next, the reaction of ethene with bromine forms a single product. Give the full name of the mechanism of this reaction. The mechanism of this reaction is known as electrophilic addition. Complete the diagram below to illustrate this mechanism. Include all relevant charges, partial charges, curly arrows, and lone pairs. So this mechanism starts off with the pi electron cloud around the double bond getting attracted towards the partial positive charge on one of the bromine atoms in the bromine molecule. And the reason that this bromine atom gets positively charged is because this same pi electron cloud repels the electrons of this bromine atom towards the opposite end of the molecule, meaning this end of the bromine molecule becomes positively charged while the other end becomes negatively charged. Now, the Br-Br bond breaks heterolytically, and so does the carbon-carbon double bond. This results in the formation of an intermediate in which one of the bromine atoms adds on to one of the carbon atoms of ethene, while the other carbon atom gains a positive charge, converting this species into a carbocation, and the Br molecule is converted into a Br negative ion with the lone pair of electrons on this ion belonging to the belonging to the or rather being the shared pair of electrons between the two bromine atoms forming the covalent bond. So this lone pair of electron is now attracted towards the positively charged carbocation. This Br negative ion adds on to the carbocation, resulting in the formation of the compound 1,2-dibromoethane. Question 15. Chloroethane can be converted back into ethane by a two-stage process via an intermediate compound X. Okay, so C2H5Cl in reaction 1 forms X, and X can form C2H6. Give the name of X. So we need to get rid of the chlorine atom present. So this should be an alkene. So removal of hydrogen from one carbon atom and chlorine from the other. So give the name of X. 2-carbon alkene is called ethene. And the formula of ethene is C2H4, or we can write CH2 double bond CH2. Suggest the reagent and condition needed for reaction 1. So in order to get rid of the hydrogen and the chlorine atom, we need to react chloroethane with NaOH in the presence of ethanol, and we need to heat this reaction mixture under reflux. So heat under reflux. Suggest the reagent and conditions needed for reaction 2. So reaction 2 is basically hydrogenation. So hydrogen is being added, so the reagent required is hydrogen gas, and the catalyst needed is either nickel or platinum. One of these will do, and the temperature requirement for this reaction is in the range of 150 to 200 degree Celsius. Question 16. The structure of H is shown. Okay, it is an alkene and it is also a primary alcohol. Both the functional groups are present in the same compound. H reacts with both cold dilute acidified potassium manganate 7 and with hot concentrated acidified potassium manganate 7. Give the structure of the organic product of the reaction of H with cold dilute acidified potassium manganate 7. So both the carbon atoms with a double bond between them will have an OH group added on to them. So we would end up with a compound in which we've got a CH3 single bonded to a carbon atom, which is bonded to a CH3 group at another end, and this will have an OH group added onto it, which will be bonded to another carbon atom that has a CH3 group on one end, a CH2 OH group on the other end, and on the third position, we will have addition of the OH group, which is the product formed when an alkene reacts with cold dilute acidified KMnO4. Give the structures of the organic products of the reaction of H with hot concentrated acidified potassium manganate 7. So when H reacts with hot concentrated acidified KMnO4, the double bond will completely break. The species on the left side of the double bond will have two CH3 groups attached to a carbon atom, to which we will have the bond formation between that carbon and an oxygen atom, which would result in the formation of a ketone. So the name of this ketone is propane 2-on. And on the other end, we would have a similar reaction taking place. The carbon atom that formed the double bond will now form a double bond with an oxygen atom. On one end, it will have a CH3 group attached to it. And on the other end, it had a primary alcohol which gets oxidized to a carboxylic group. Thus, this compound is a 3-carbon carboxylic acid, which is propanoic acid, having a ketone group on the second carbon atom. Complete the reaction scheme to show the mechanism of the reaction of H with bromine to form J. Include all necessary curly arrows, lone pairs, and charges. So this reaction would start off with the pi electron cloud on the double bond being attracted towards the positive charge on one of the bromine atoms, which was induced because of the pi electron cloud itself. This results in the Br-Br bond breaking heterolytically and also the carbon-carbon pi bond. So the intermediate that would form would be a CH3 group attached to a carbon atom with another CH3 on it. This would be attached to a carbon atom with a CH3 and a CH2OH group attached to it. The one with two CH3 attached to the carbon atom will have a bromine added onto it according to the way in which the double bond broke heterolytically, and a positive charge will be present on the carbon atom that will be attached to CH2OH. So this is the carbocation that would form, and also the Br negative ion that would form due to the heterolytic fission of the bromine molecule. The lone pair of electrons on the Br negative ion will be attracted towards the positively charged carbocation. This Br negative ion will be added onto the carbocation, producing a compound with two bromine atoms present on two adjacent carbon atoms, between which there was a double bond present before the reaction mechanism took place. Explain the origin of the dipole on the bromine molecule. The proximity, proximity means the closeness or close location of the pi electron cloud of alkene induces a dipole onto the Br2 molecule. So when the dipole is induced, then the pi electron itself gets attracted to the pole which is partially positively charged. J is formed as an equimolar mixture of isomers. State the type of isomerism shown by J. So J has all single bonded carbon atoms present, so J would show optical isomerism. Draw the structures of the two isomers of J. So the two isomers of J would be mirror images of each other and would contain four different groups on four different positions on the carbon atom. So on one of these positions, we can have the presence of the CH2OH group. On another position, we can have a bromine atom attached to the chiral carbon atom. This would be the same position on both the optical isomers. So we have one bromine atom present on one position. On the third position, we can have a CH3 group present on the chiral carbon atom. And on the fourth position, we can have the carbon atom with the other bromine attached to it. So that would be a carbon atom attached to a CH3 group, a bromine atom, and another CH3 group. And the same group would be present on the opposite side of the other optical isomer, having two CH3 groups present and one Br atom attached. So these are the two optical isomers of J. Question 17. Propene may be polymerized. What is the essential condition for such a polymerization. So polymerization would require the presence of a catalyst. It would require high temperature, and it would require high pressure to carry out the process of polymerization. The disposal of waste polypropylene is very difficult. Give one important reason for this. So, polypropylene is an addition polymer, so it will not have any ester or amide bonds present in it, so it cannot be broken down by the action of microorganisms. Thus, they are non-biodegradable. So, polypropylene is not biodegradable, meaning cannot be broken down by microorganisms, and if burned it will form harmful combustion products. Question 18. Two derivatives of ethene which have been detected in dust clouds in space are acrylonitrile, which is 2-propene nitrile, and vinyl alcohol, which is ethanol. Ethanol. Like ethene, acrylonitrile can be polymerized. The resulting polymer can be used to make carbon fibers. Draw the structural formula of the polymer made from acrylonitrile showing two repeat units. So the double bond opens up and the monomers are added together in the polymer chain. So acrylonitrile will have one carbon atom with two hydrogen atoms attached to it, and the other carbon atom will have a CN group on one end and a hydrogen group on the other. So this is the start of the polymer chain, and we need to make two repeat units. So this is one repeat unit. The other repeat unit will also have two hydrogen atoms attached to one carbon atom and a hydrogen and a CN group attached to the other carbon atom. These are two repeat units of polyacrylonitrile. What type of a polymerization is this reaction? This is an example of an addition polymerization. Question 19. Butene can be polymerized to give polybutene. Draw the structural formula of a portion of the polymer chain in polybutene showing two repeat units. So the structure of butene is CH3, CH double bonded to CH and then CH3. So when we make a single repeat unit of polybutene, we will have two carbon atoms with a single bond between them. One carbon atom, in fact, both the carbon atoms will be attached by a CH3 group on one end and a hydrogen atom on the other. This is one repeat unit. The other repeat unit would have a similar structure of CH3 being attached to both the carbon atoms on one end and hydrogen on the other. So these are two repeat units of polybutene. Question 20. Chloroethene can be polymerized to form a polymer commonly known as PVC. So the formula of chloroethene would be C double bonded to C. On one carbon atom, we will have a Cl and a hydrogen group. On the other, we will have two hydrogen groups attached. So this is the structure of chloroethene. Draw a diagram of the structure of PVC including three repeat units. So we need to make polyvinyl chloride, and chloroethene is also known as vinyl chloride. So we start off with the first repeat unit having two carbon atoms. one carbon atom with a chlorine and a hydrogen, the other carbon atom with two hydrogen. This continues into the second structure, second part of the structure, having two carbon atoms, one having a chlorine and a hydrogen attached, the other having two hydrogen atoms attached. Then we come to the third repeat unit of PVC, on which we have a carbon atom with a chlorine and a hydrogen on it, and a carbon atom with two hydrogen atoms attached to it. So the color codes represent the three different repeat units of PVC, and the entire structure shown here is a polymer called polyvinyl chloride.